the Aurora Borealis. It's common knowledge that the Aurora Borealis, or the Aurora Australis, in the southern hemisphere usually occurs in the polar regions of the world and is rarely seen anywhere else. But why? Why does this spectacular phenomena typically occur in the extreme northern and southern reaches of our world? Why is it rarely seen beyond its polar home? What does the aurora have to do with magnets? And lastly, what in the wide world of weather is the Aurora Borealis?
In order to understand what exactly is going on, we must first take a look at what is happening over 1,800 miles below our feet in the Earth's core.
The Earth's core is split up into two sections, a solid inner core and a liquid outer core. It's this liquid outer core that we need to focus on. Now the inner core is much hotter than the outer core, and because of this, the nickel-iron material at the bottom of the outer core moves towards the colder top where it cools and begins to sink back down and warms up again to start the process all over.
We call this process convection, and it's the same process that happens here in the lower portions of our atmosphere to produce thunderstorms.
It's this convection of the nickel-iron outer core that creates a giant magnet within the Earth whose magnetic field radiates outward into space for tens of thousands of miles. Now let's take a small magnet and sprinkle some iron filings around it. What you should see is something like in the picture where the filings will align themselves to the magnetic field in a circular shape. But if we were able to do the same thing with the Earth's magnetic field, it would look something like this. A weird sort of hemisphere on the front with a tail like a comet on the back. But why? Why is it shaped like this, but not the circular shape that we saw on the smaller magnet? Our answer lies about 93 million miles away with our closest star. See, the sun has a hidden danger in the form of solar winds. Solar winds continuously flow from the sun in all directions as plasma with an embedded magnetic field that radiates out from the sun and speeds towards Earth at speeds of over 500 to 800 kilometers per second, causing the magnetosphere, which is where the magnetic field is located, to bow back in the shape that is seen in the picture. But this stream of plasma is extremely dangerous to the Earth's atmosphere, as without the Earth's magnetosphere, solar winds can strip the atmosphere from the Earth, exposing the Earth to the harmful effects of UV and other high-energy radiation.
Now it's through these solar winds where we get our beautiful and stunning auroras, but also what are known as geomagnetic storms.
See, as fast-moving solar winds impact the Earth's magnetosphere, it charges up the magnetosphere, causing an increase in plasma movement and an increase in electrical current both within the magnetosphere and the ionosphere.
These changes can wreak all sorts of havoc with communications here on Earth and with orbiting satellites.
During a storm, high-frequency communication systems that rely on the ionosphere to reflect signal back to the surface for long-distance communication can instead be absorbed, causing many communication issues. GPS navigation can be thrown off by miles as the signal can be disrupted. Power grids can take a hit as geomagnetically induced currents can cause transformers to overheat. Even the hardware in a satellite can potentially be damaged during a geomagnetic storm.
But enough talk on how the sun hates us and satellites. Let me get to the point where I actually go over what causes the aurora.
As solar winds compress the magnetosphere, it changes the trajectory of the charged particles in the form of protons and electrons of both solar winds and plasma in the magnetosphere to interact with the upper atmosphere. When these particles interact with the upper atmosphere, they cause the nitrogen and oxygen molecules in the atmosphere to be charged with energy. This energy is then released in the form of visible light, finally creating the dazzling and spectacular display we know as the aurora.
Now the question remains, why do people here in the United States, excluding Alaska, almost never see the Aurora Borealis?
Well, in order to have a visible aurora here in the US, we must have a strong geomagnetic storm. In order to have a strong geomagnetic storm, we must have a strong solar event in the form of a coronal mass ejection. Coronal mass ejections are essentially titanic chunks of the sun's outer atmosphere containing millions of tons of plasma in a strong magnetic field being shot out into the solar system. Even though they are slow compared to solar winds, only traveling at around 277 kilometers per second, they can cause even more disruption to the Earth's magnetosphere and cause auroras to be visible well beyond their polar origins, including being visible here in the US. Aurora Borealis Fast Facts! The name for the Aurora Borealis was chosen by the famous astronomer Galileo Galilei in 1619 and comes from the Roman goddess of dawn, Aurora, and the Greek name for the north wind, Boreas. The Earth's geomagnetic poles are not actually directly in line with each other, because the quote-unquote magnet within the Earth's core is not a true dipole magnet. Both poles have also been moving over time. One of the largest geomagnetic storms occurred on September 2nd, 1859, and is known as the Carrington event. This geomagnetic storm was so strong that it caused auroras to be visible throughout the US, Europe, Japan, and Australia, along with being so extraordinarily bright that the New York Times reported that, quote, at about 1 o'clock at night, ordinary print could be read by the light. Even stranger, 2 telegraph operators, one in Boston and the other in Portland, Maine, were able to continue a conversation on the telegraph after both sides disconnected their power source. The Earth is not the only planet in the solar system to have auroras. The 4 gas giants, Jupiter, Saturn, Uranus, and Neptune, have all been observed to have auroras.
And that does it for this episode of What in the Wide World of Weather. Now this episode has been extremely hard to write. Just the sheer complexity of geomagnetic storms, solar winds, the magnetosphere, and a whole host of other things drove me crazy. A lot of what has been said in this episode has been grossly oversimplified. But with that in mind, join me next time as I will be taking a look at hurricanes. And remember, the more you know about weather, the more you can just sit back, relax, and, well, enjoy the view.